Okay, welcome back. What we're going to be looking at here is doing some curve fitting or data regression using Matlab. So we'll start out here with, I got a blank Matlab here, and what I'm going to do, I've actually got a script file that I created to run this, but I'm just going to be grabbing the values out of the script file and pasting them into Matlab workspace, or Matlab command window, just so we can illustrate it, one step at a time. So I'll paste these in. So basically what I've done now is I've created two variables. X starts at 1, increments by 1, and goes up to 15. So I've got 15 values of X evenly spaced. I've got some Y values that I've created. There's 15 of them, and it's just a single row vector. You can see that it's on 3 lines here, but what I've done is I put the ellipsis there, the 3 dots on the end of each line that tells Matlab that's a continuation, so it doesn't treat it as a matrix or anything. It's just a 1 by 15 row. So I have the data. What's the first step I do? Well, I need to plot that data. Plot X comma Y. See what it looks like. Well, here, let's even better. Let's make rather than a line, let's make a just use an asterisk so that we can see what is the actual data. Turn the grid on. So if I look at the data, there seems to be a pretty good correlation between the input and the output. So I'm willing to do a curve fit. Now I can't guarantee causality, obviously. Correlation and causality are two entirely different things. But given that we have correlation, and assuming that these numbers came from some sort of engineering data set where we have reason to believe that there is a correlation or there is causality, then it's reasonable to proceed. It's not going to be a perfect fit. You can see there's some wiggles in here, but we'll see what we do. So the first tool we're going to use is called Polyfit, P-O-L-Y-F-I-T, and I give the function Polyfit 3 arguments. I give it the X values, the independent values, Y values, the dependent values, and I give it N. And let me just pop this up. So I say that A equals Polyfit X, Y, N. Okay? So what this will do, it will take the independent variable X, the dependent variable Y. This argument here is the order of the polynomial. So if I make that, for example, 2, a second order polynomial, what I'm going to try and do is fit a polynomial of the form A1 plus A2 times X plus A3 times X squared, Y equals. So I'm creating a polynomial up to a squared term, a second order. That's the N there. And it's always this form. And these coefficients A1, A2, A3 will end up in this output from the command A. And this will be the output of our regression. And these are the values we determine. Whatever values of A1, A2, and A3 are best to fit this equation. So let's go back to our script file. And here I set n equals 2 because I could have put the number directly into this polyfit command, but by putting it separately in this script file, it stands out. That's where I need to fix it if I want to change it from second order to third order. And rather than doing a copy and paste, I'm going to right click, evaluate selection, and it just evaluates it on its own. And we go to the Matlab command window, and you can see that it's set n equals to 2. That's in our workspace. It did this polyfit command, and since I didn't put the semicolon there on the end of that line of polyfit, I now have the values of A. So let's see if I can Control C. So there's my numbers pasted in from Matlab. So my regression now becomes, okay, y equals minus 0.014, I'm only going to a couple decimal places, plus 0.39 x plus 0.07, I'm a little overzealous in my rounding there, 0.07 times x squared, and that's my equation that I will use if I want to do it at all. And these are the values that gave me the best fit in the least squares way. So, is it any good? What happened? You know, how does the line match the actual data? Well, I have coefficients. What do I do with them? Well, one thing I can do is I can create a line using those coefficients. So what I'll do is I'll look at the minimum value of x, the maximum value of x, and I will create a vector, I'll call it xx, that starts at the minimum value of x. It increments by the difference between the maximum and minimum divided by 100, so I get about 100 points, and it ends at the maximum value of x. So that's just pretty much straightforward creating variables. So I should have created those variables, and then we'll use this function here, polyval. What polyval does, and I'll pop back over here for a moment. Polyval, if I say y, I'll call it yy so you don't get confused, equals Polyval of xx. Those are the x values I want to put into this polyval function, and I give it the, I'll make sure I'm doing this in the right order because I always have to click on the help myself because I can never remember. Okay, I was doing it backwards. So the first thing I give polyval is the array with coefficients, and this array, if you remember, had 3 terms in it. And I give it a set of x values, call it xx, at which to evaluate that polynomial. So what it will do is substitute that values for xx into, for every value of xx, it's xx, it'll plug in each value of xx into this polynomial and come up with the corresponding value of yy. And then we can plot those values. So we give it the command yy equals polyval axx. So now in Matlab we should have, let's take a look. We have our variables xx and xy. There's 101 terms in each. And we can plot x and y, my original data, with the stars. And at the same time, we'll give it another xy pair, xx and yy. We'll make that a red line right here. Okay. Put a grid on it, put a title on it. And here in the title, let me evaluate this. In the title, since I'm kind of making this a generic script file, you know, I put n equals 2 up here for the order of the polynomial. Here I'm evaluating that value of n, converting it to a string, and putting it together with this text order fit. So the title of my plot will be second order fit, or 2 order fit really. And as I change n, if I want to do a 3rd order, 4th order, 5th order, whatever, it'll change the title of the plot automatically for me, which is kind of handy. So here it says it's a 2 order fit, so I know what it is. The stars are the original data points, and that red line is my curve that I fit to it. Not too bad, right? It looks reasonable. Okay. What do we do with it? Now I you know, at this point I have an equation for a line. You know, there's the coefficients in Matlab, and of course we had the coefficients right here that we wrote out here on Windows Journal. So now I have an equation for the line. I can pretty much do what I want with that equation, but we should really do a little bit of analysis to say, it looks good by eye, but is it good generally? Well, normally when we're doing curve fitting and statistics and things like that, we'll do an analysis of the residuals. That's the difference between the point on the line. And here, let me do this. Hang on. There's that, and I'll get my snip tool. New snip. Of course, cancel. Of course, this is not on top. I don't know why Windows decides to rearrange things on me. So let me just copy this into something I can draw on. So what the residuals are is if we were to look at the points on this line that correlate to the x values that we had originally, we can look at the difference between the line and the point, and that gap, if you would, is the residual value. Okay, so at each point we have some difference, and the smaller the difference, the better our fit, and the smaller the sum of squares of that difference in particular, the better our fit. So to calculate the residuals, we will evaluate our polynomial at each of these points and subtract the results from that evaluation from the actual results. So I will use the polyval command again, and I'll give it the same coefficients a, but this time I'll give it my original x values that I used, and I'll take the regressed values, the expected values from the polynomial, subtract y, which are the actual values, and I get my residuals. Evaluate selection, and I should have in Matlab here just a whole bunch of numbers, and you can see some are positive, some are negative. That's a good thing. On average it should be 0. I can do some statistics. I can calculate the r² statistic, evaluate selection. Now how do I do that? Well, I'm calling a function r². Now in this case, r² is not a built-in Matlab function like Polyfit and Polyval. It's actually one that I wrote. So I have to have this function r² either in the same directory as all these other files or somewhere on the Matlab path, which I'm not going to get into at this point. But so for now, if you just put these files in the same directory, everything works fine. But my r² statistic here is 0.9647. So basically about 96% of the variation in the y values are explained by the regression, leaving a little bit less than 4% of the variation is just due to noise or things or due to lack of fit. That's the best way to put it. So that's another indication we've got a reasonable fit. We can do other calculations like calculating standard errors and things like that. I don't want to get into that as a result due to time here. But one thing we always do is I want to plot, since I have this value of the residuals at each of these x values, I'm going to plot x, comma, resid, and I'm going to make those stars again. And I'm going to look at my residuals as a function of my independent variable. And let me turn the grid on. So there's my plot. And let me put that into something here that I can draw on. Draw on easily. Okay. So there's my residuals. They're centered around 0. They don't look that bad from that perspective. The question we'd be asking at this point, is there an obvious pattern? as I look at it, and this is quite frankly the first time I've looked at this data, this particular data set, so I do know how I generated it, but it's okay. I'm kind of seeing a shape here. Maybe it's just me, but it seems to be there. And when I see a shape in the residuals, that one's not so bad. Sometimes the you'll see a shape that looks that looks like this, or looks like this, or something like that, where they're real obvious. Those are all indications that maybe the polynomial wasn't the best fit, whether it's because it's a polynomial itself, or because or because we just chose the wrong order. It's hard to say. So thank you. Erase that. So I'm kind of wondering if there isn't something going on here. Something just doesn't look right. Even though we've explained 96% of the data and our original plot didn't look that bad, I'd probably want to look into this data a little bit further and put some thought into it and see what I could figure out. Now, if we just want to do dumb regressions here, I can say, well, maybe it's just higher than second order. I'll make it a third order polynomial, and I'll just run this script file by clicking on that triangle rather than cutting and pasting. And the fit, again, the fit looks pretty good, just eyeballing it. I'll create a new figure, figure 2, and I'll plot my X residuals, and I'll turn the grid on, and I'll go to figure 2. That's looking better, I think. Let me pop this up again. New. Oh, come on. Cancel. New. Okay. So, possibly, is there a curve that looks like this? That's a stretch. So I'm feeling, I got some points way down here. From just a purely, look at the residuals, this doesn't look like a bad fit. Now, strange things can happen. Does this match the behavior of the real world? If we look at, I'm going to do is, let me go back to Matlab, and I'll say XX up arrow. I'm going to go from increase the range here, min divided by 2 to max times 2. So now I'm going to create my minimum and maximum in a range beyond what my normal data what collected was at, and then I can do my polyval and my plot, evaluate selection, and okay, I guess I didn't go very far, but you can see, once I get beyond where I created the data, once I get out into this region, you really have to ask yourself, does this make sense from an engineering perspective? And it probably doesn't. It's when you're fitting polynomials, any extrapolation is risky. You might extrapolate out to here or something like that, or down to here. But does it in general make sense that I'm seeing a curve that kind of looks like that? Does my physical reality support this idea that's going there? Probably not. And even if it did, I would not trust this regression out at these ranges just because it's just a blind fit. Unless I had some real engineering understanding that says this is this way this data is supposed to fit, then I wouldn't do that. I would also, cancel. I would also, if I had other variables, other data in this data set, I would plot the residuals as a function of anything and everything I had available, looking for correlation. Because if I see correlation between the residuals and some parameter that I did not include in my regression, then that would lead me to suspect that that there's something in the data, that parameter that's lurking there that I didn't take into account. So for those of you in my class, this function polycurve was included with homework 1 with some different numbers in it, so that a good template for you to work from and to fit the curves to the data I've given you in the homework. If this video is public, so if somebody's just watching this, hopefully you couldn't go back, pause it, and read the screen well enough to duplicate the results if you want. One other, of course, this polyfit obviously fits a polynomial. What if I have two independent variables? If I want to fit a surface, polyfit isn't going to do that for us. So I'm going to pop into another example I have here. This is using the backslash operator in Matlab. It's another way of fitting data. So let's walk through this fairly quickly because a lot of this is pretty much the same thing we did. Okay, I'm initializing the random number generator. That's not important for this demonstration. I'm creating a random set of 500 x variables, a random set of 500 y variables. Now in this case, x and y are both going to be the independent variables, and I'm going to create this dependent variable, which is the surface. An x is a 3D surface. Okay, and I'm also throwing in some error here using that random function, so it looks more like real data, which always has errors in it. And I'm fitting it according to this equation: 0.82 plus 0.45 times the log of x plus 1.33 times y times the error. So it's kind of a weird surface that we're drawing here. Okay. Let me just evaluate this to create this data. Oops. Before I do that, let's go back here and type clear to clear out all the old data, and CLC to clear my screen there. Now that way I won't get old and new mixed up. Evaluate that selection. So now I've created something, and why did you bink at me? Oh, I must have cut off the last evaluate selection. There we go. Okay, I cut it when I didn't quite catch the whole end of that word. Okay, so now what I want to do is create a regression. So what I'm going to do, let me go into Windows Journal, start a new page. I've got x, y, okay, I've got these variables I've created, and somewhere up here is some surface that sits on top of x, y, okay, and I'm going to try and fit to that surface. So what I'm going to do here, but I need to come up with an equation. It's not a polynomial. There's x, there's y, there's different things in this equation. So what I'm going to do is, let me copy this out of the editor here, because this is not going to be obvious. I'm going to create a variable I, which is just ones, okay? So, and I'm going to create this variable states here. And let me copy this, paste, okay. So I'm going to create an equation where it's going to be of the form y equals some constant value. This is the I, because I'm just fitting it to 1. So that'll be a1 plus a2 times x plus a3 times x to the fourth, and I use the dot power dot caret form, so it's a element by element to the fourth, not a matrix arithmetic, plus, I should have started further to the left, I'll continue this on, a4 times y plus a5 times y squared. Okay, so by creating this variable of states, each one of these is a column vector, which corresponds to each entry here, and I have a column vector of my measured y values, which are the points on the surface, and I will use the backslash operator to do a regression and fit the coefficients a1, a2, a3, a4, a5. And this can be, you know, here I've used two different variables. I've made a pretty arbitrary equation here. You know, it's x and x to the fourth, y and y squared. I could have thrown in logs and things like that. And, you know, we're assuming that I don't really know how the data was generated. But if we were to go back and compare here, you know, obviously this equation that I'm setting up by creating these a matrix of state vectors does not match what I did here, because I used the log of x. I didn't use x to the fourth. I didn't use x. I didn't use y squared. So it's going to be a not perfect fit, right? But that's okay. We'll just see how it looks. So I can create those states, and I will use the evaluate selection, this size command, to just get the number of states, just so I have that. And now I will use the backslash operator. And let me go to Matlab. Help. Ops. And we go back up here and we see the backslash or left matrix divide. I can click here and it tells me what that really does in the help. A backslash B is a matrix division of A into B, which is roughly the same as inverse A times B, and it explains how it's calculated. But essentially, if we get down to here, if A is an m by n matrix, etc., and B is a column vector or a matrix with several such columns, then x equals A backslash B is the solution of the least square sense to the under or over determined system of equations A times x equals B. This is the equation I want, right, where I have these coefficients A, I have my independent variable or independent states, and then I have a result. So we're solving that equation using the backslash operator. So it's essentially like doing a least squares regression. So I can evaluate this, and I'll just evaluate it without the semicolon. And it tells me that my coefficients are here. We'll see, and going back to Notepad, put it over here. Paste. So I can't read the last one. So what we're saying is that we expect y equals minus 0.51 plus 2.21 times 2.21. Oops. Doesn't help when I drop my pen. 2.21 times x plus, or minus 1.06 times x to the fourth plus, and I lost those last couple, 1.27 and 0.01. 1.27 y plus 0.01 y squared, if I didn't get the signs wrong. So now I have this equation here in x and y. Oh, this shouldn't be y here because I'm using y in multiple places. That's my dependent. Now, a dependent variable, and I apologize if that created some confusion earlier. We could have called this z, I guess would have been a sensible thing to do. And then on my graph, if I have z in that direction, z. So now I have an equation for a surface that's the best fit in the least squares sense given this form where we have a constant offset. We have it as a function of x to the fourth, y, and y squared. Now it's not going to be a perfect fit because that's the wrong form of the equation, but that's the one we chose to fit, and we'll just see how it works. So I have my coefficients back here. Again, I can do the residuals, expected states times the coefficients, gives me the expected values. The residuals are the expected minus dependent variables. I can calculate the residual sum of squares, degrees of freedom, standard deviation of the error, some more statistical analysis. I'm going to skip that for right now. And what we're going to do is, I better not skip it all. Basically, I can calculate the standard deviation of the error given the sum of squares of the residuals, the degrees of freedom, and the variance of the error. And the standard deviation of the error is 0.18, so there's, gives me that statistic. I can do some sum of, basically what this code here will do is calculate the standard errors of the different coefficients so we can see which ones are significant. And this is just cookbook out of a statistics textbook. I'm not trying to teach statistics. Okay, but what it tells me is that the coefficient, the first coefficient minus 0.5, standard error of 0.008. So the standard error is a lot smaller than the coefficient. That coefficient is probably significant. Coefficient is 2, standard error 0.01. That looks good. Negative 1, 0.02, we're good. Same thing here. Now this last one, this term of y squared that I had in my states, remember there was no y squared in my original data creation, and you can see the coefficient of 0.13, a standard error of 0.018. Chances are that coefficient is not significant. It statistically doesn't mean anything, and we can probably remove it from our regression if we want, and life will go on. Calculate the R squared statistic, evaluate selection, and I come up with an R squared of 0.90, so 90% of my shape is defined by this regression, leaving 10% due to unexplained by the regression effects. Part of that unexplained effect is the fact that we didn't use the right form. And here we're going to do a 3D plot. I'm going to use this mesh grid to create a grid of points, calculate the values, the z values at each of those points, etc., and make that three-dimensional plot. And if you want to see that, you can kind of pause the video and read it off the screen. In the interest of time, I'm going to kind of move it on. But now I have a 3D plot with all those asterisks being the points And if I click on this little revolving thing, I can revolve this plot around and try to see how it matches. And you can see it doesn't have the right shape, right? It kind of fits in a general way, but the shape of the surface and the shape of the data don't really match. And that, again, that tells me that I've done a pretty crummy job of picking an equation to fit the data, which we knew up front because we knew the equation to generate the data. Okay? And from here, what I should do is, if it wasn't so obvious that this is wrong, I would do a analysis of the residuals as a function of x, an analysis of the plot of the residuals as a function of x, plot of the residuals as a function of y, and I see that it just plain doesn't fit, and I would go back and try to go back to my engineering principles and understand the system better and say, what makes sense to fit to this data? Presumably this data came from some physical, electrical, pneumatic, hydraulic system, and it should have some sensible behavior that we could understand based on understanding of engineering and physics, and we should be able to come up with a different equation. But for the purposes of here's the mechanics of doing this kind of regression stuff, I think I've covered that. Thank you I hope this was helpful. And well, the next session, the next video, we will get into using Simulink. We'll do some basic models, and then probably we'll do a more extensive model just to give you guys a little more practice for my class. So, that last one would be considered optional. But, well, we'll get there when we get there.